This lecture is on some applications of exponential growth, exponential models. There's quite a few. We'll start off with just formulas for discrete and continuous compounding of interest. For discrete means individual compounding of interest, such as monthly, yearly, daily, something like that, whereas continuous is this theoretical point where it's happening constantly. So for discrete compounding, the amount you have at a given amount of time is equal to the principal P, which you start with, times 1 plus the annual interest rate divided by the number of times you compound per year times, or to the power of the number of times you compound times the number of years. So n is the number of times you compound per year, t is the number of years, r is the annual percentage rate, p is what you start with, a is what you have at time t. For continuous, much simpler formula. The idea is that as n approaches infinity, you have what's called a limit, something we'll derive later in calculus, that ends up bringing in e, and so the amount you have at time t is the principal times e to the rt. Again, r is the annual percentage rate, and t is time. If you want to find out how fast your money takes to grow by a certain amount with continuous compounding, we can look at it this way. This is our continuous compounding formula, and let's suppose we want to see how long it takes for our money to multiply by n times. So as opposed to, say, just doubling, we want to see how long it takes to get up to n times. And so if we start with p, then we would have p times n for our amount, because we take our original amount and multiply it by n. We can divide p from both sides. We take a natural log of both sides, and then the amount of time it would take to multiply by n times is ln n over r. So the natural log of the number of times you want to multiply your money by divided by the percentage rate. Next, we'll look at a couple half-life models. Half-life is often used as an application when we discuss decay of radioactive isotopes. So two different ways to look at it. We have the amount at a given amount of time is A naught, which is your initial amount, times 1/2 to the t over tau, where tau is your half-life. Sometimes I use the Greek letter tau for half-life, sometimes I use t sub half, so either one of these. Another way to look at decay and with half-life is y is equal to a naught e to the kt. A naught is again the initial amount, and k is your decay constant. So our half-life tau, or t sub half, and decay constant are related in the following manner, which I will show in a moment. Depending on which you want to do, sometimes one model is easier than the other. Here's how they're related. If we have a of t is equal to a naught e to the kt, we know that at time 0, we have a naught e to the k times 0, which is simply a naught because e to the 0 is 1. So again, we start with our initial amount, a naught. Now, half-life simply means that after that time has elapsed, you have half of what you began with. So if you plug in the half-life t sub half, we have half of which we began with. So we have half of a naught equals a naught e to the k times t sub 1/2, or tau. So we plug in that time half, and we have half of what we started with. Divide off a naught from both sides, and what we see, of course, the initial amount does not matter here. We can take a natural log of both sides. This is simply k times t sub 1/2, because the ln and d cancel. Now we have the half-life is equal to ln half over k, and finally we can write it as negative ln 2 over k by simply doing a little bit of fooling around with the exponents and properties of logs. So this equation here, t sub 1/2 is equal to negative ln 2 over k. That's basically a way to relate half-life and decay constant. Okay, look at an example in the textbook. Here we have some exponential growth. The idea is that after 2 days there's 100 fruit flies, 4 days there's 300 fruit flies. How many flies will there be after 5 days, assuming again we're increasing exponentially? And so we're given 2 points, time 2, 100 flies, time 4, 300 flies, and then we have time 5, how many flies. And so this is how we can set it up. We have our basic model, a of t is equal to a naught e to the kt. We have two variables. We have a naught and we have k. We don't know what the initial amount is yet. We don't know what this growth, the constant is, or decay constant, as the case may be. But we do have 2 points, and so with 2 points we should be able to find out these two constants. So we plug in each point. So we have 100 is equal to a naught times e to the 2k. We plug in this point. We have 300 is equal to a naught e to the 4k. 2 equations, 2 unknowns. The easiest way to handle this is eliminating a constant by simply dividing. I divide the bottom equation by the top. 300 divided by 100 is 3. The a naughts cancel when you divide, and e to the 4k divided by e to the 2k is e to the 2k. You subtract exponents. So I take a natural log of both sides. Ln 3 is equal to 2k. And so k then becomes ln 3 over 2, which is approximately 0.5493. So we have one of our two constants between a naught and k. Well, now that I've got one of them, I can use either one of these points. I'll use the first point. 100 is equal to a naught e to the 2k, where k is now 0.5493. And I go ahead and I solve for a naught. I didn't bother getting out the calculator to see what it was. So I have k, I have a naught, so I have my model. A of t now is equal to a naught, this big number, e to the kt. And finally, if you want to find out how many fruit flies there are after 5 days, well, we just plug in 5 for t. So we have 100 over e to the 2 times 0.5493, and then e to the 0.5493 times 5. Another book example, we have the logarithmic model used for Richter scale intensity of an earthquake, really magnitude of an earthquake. Magnitude and intensity are slightly different. So using some minimum baseline magnitude for comparison, we have the Richter scale value is equal to log base 10 of I over I naught, where I naught's that base value. And so comparing these, the Peruvian and Mexican earthquakes, we have our I naught's 1, we have R is 8.4 for this earthquake in Peru, and so we plug in 8.4 for the Richter, and we plug in 1 down here for I naught, and we end up getting that this is the intensity of the earthquake. If it's a 7.6 earthquake instead, then we plug in 7.6, and instead of 10 to the 8.4, it's 10 to the 7.6. Next, we'll look at number 10, where we have continuous compounding. We know we have an initial amount of $1,000. It takes 12 years to double. We'd like to find out the annual percentage rate and then how much we'll have after 10 years. So we're given the fact that it's an exponential model, $1,000 to start with, 12 years to double. So here's our information, continuous compounding, principal's 1,000, doubling time 12 years. So we know that if the doubling time is 12 years, then after 12 years, well, we have $2,000. So we plug in 12 for t, 2,000 for our a. We can divide by 1,000, take a natural log, and so of course our annual rate then is ln 2 divided by 12, which comes out to 5.8%. And then we have our model of 1,000 e to the 0.05776t, because actually the 5.8% was really more accurately 0.05776. And then at that point we can find out how much we have after any number of years. Number 20, we have a radioactive decay example. We have radium-226 with a half-life of 1,599 years. We'd like to know the initial amount, and we know that after 1,000 years we have 1.5 grams. So we're trying to get a naught, and we have a data point that says 1,000 years, 1.5 grams, and we also know the half-life, 1,599 years. So this is a way to look at it. I've got it up here with the base of a half and down here with base e. We can look at it both ways. And so we know that our half-life is 1,599 years, so I can plug that right in for our tau. And after we have 1.5 after we plug in 1,000 years, and so I plug in 1,000 for time, 1.5 for our amount after 1,000 years, and then simply you divide by 1/2 to the 1,000 over 1,599, and whatever this is will be your initial amount. Alternatively, we can use the base of e, but we'd still, of course, have a half-life of 1,599, an initial amount of 1.5 grams, just a little bit more work actually this way. So we know that after 1,599 years, we have half of what we started with. We divide both sides by a naught. This is just like the way we derive the formula between half-life and decay constant. I take a natural log of both sides, and I solve for k, and it's ln half over 1,599, which is about this. So now I have this model. Well, now I can use the fact that I have 1.5 grams after 1,000 years, so I plug in 1.5 here, plug in 1,000 for time, and then I go ahead and divide, and you'll see that these expressions are actually equivalent. Lastly, we want to find an exponential model, y is equal to a times e to the bx, which passes through these 2 points, 0,5 and 4,5. Well, we have two constants, we need a and b, and we have 2 points, so we simply plug them in. So I have half for y, I have 0 for x, I have 5 for, this already gives me y is equal to 1/2 e to the bx, because of course e to the 0 is 1. When you have a y-intercept like this, it makes it even that much simpler. Now I can use my second point, 4,5. So 5 is equal to 1/2 e to the 4b. I can multiply both sides by 2, take a natural log to solve for b, and then divide by 4. So b is 1/4 ln 10, approximately 0.5756. So I've got my A is a half, I've got my B as 0.5756, and there's my exponential model, which passes through those 2 points.